Go ahead. Let's start 5-5. Okay. So again, we're going to do 5-5 today. We're going to do 6-1 tomorrow. We're not going to have 5-5 and 6-1 on the test next week, but they will be tested on in the future. In test 2, those will both be topics in there, and they're important topics. Particularly 5-5 is a very important topic. So 5-5 is the substitution rule. So right now, while we've been talking about integration, if we tried to integrate a problem that looks like this, our integration rules are not going to be help to us, right? I can integrate 2x. I could integrate the square root of x, but I don't have any antiderivative rules to handle like a function times a function or a function nested inside of another function, right? So what do I do with this? Seems like we're stuck, like there's nothing we can do. Well, as long as these two functions kind of meet certain criteria, we can do this. So recall up to this point, the only antiderivative rules we have are for derivative shortcuts. We don't have any antiderivative rules to deal with a chain rule or a product rule or a quotient. And now, as we go on, we're going to be looking at kind of figuring out how to do the antiderivative for some of those things. Today, we're going to be talking about the chain rule. So what we're going to be talking about today is how to find the antiderivative of a chain rule derivative. Okay? So, yes.
But wouldn't this be so this would technically be a chain rule problem?
It is the result of a chain rule derivative.
Oh, got it.
So recall the chain rule, which says that f of g of x is f prime of g of x times g prime of x, right? That was our chain rule derivative or definition. So what that says then is if I want to integrate that side, I should be able to recover my chain rule function, my original function that I had before I did the chain rule to it, right? Everybody kind of okay with that idea? So that's the idea here. So if I have some function and I'm integrating that function and it has the form of f of g of x times g prime of x, that's something that I should be able to do an antiderivative of by applying, undoing a chain rule. Okay? So our formal statement here we say is the substitution rule. So what we're going to do is we're going to say, okay, if I'm integrating f prime of g of x times g prime of x, if I say, what if I substitute u in for g of x, and if I do the derivative of u with respect to x, that's just going to be g prime of x, right? And if I multiply both sides by dx, we have that g of x is u, and g prime of dx is du. So we can change that integral into just the integral of f prime u times du. So that is now just one function with a single variable inside of it. We've eliminated the product and we've eliminated the composition. This now should be something I can do with just a straight antiderivative rule. That's the idea. This is called U substitution. Our textbook calls it the substitution rule. I call it U substitution because, well, when I did this, that's what we did. But the idea is we're going to take that g of x and replace it with a u, and we're going to take g prime dx and replace it with a du, and we should have everything we need then to integrate with just one of our anti-differentiation rules. So let's go back to that original problem we looked at, the 2x times square root of x squared plus 1. Let's try doing this with that, just to kind of get a feel for how that's going to work. So what should be my g of x? What should be the thing I'm going to substitute in for u? 1 plus x squared. Excellent. Not including the square root, because we want the function inside, right? We're still kind of looking for function composition, just like we would for a chain rule. So if I do du dx, then what is the derivative of u? 2x. And I'll just multiply both sides by dx. And my u is 1 plus x squared. And my du is 2x dx.
Oh, I get it.
So I've substituted 1 plus x squared for u and 2x dx for du. And now, can we integrate the square root of u?
Yes.
Yeah, right? I'm just going to think about that as u to the 1/2. What's the antiderivative of u to the 1/2?
U, 3 over 2 over 3 over 2 over 2.
Plus c. Thank you. So that's going to be this, right? Yeah. And then we just put our u back in. Yeah. Done. And if you wanted to, you could go back and check. If you took the derivative of that function, you should get 2x square root of 1 plus x squared. And you will. Isn't that lovely?
Yes.
Like you took something, it's like, how am I going to integrate that? And in fact, you didn't really need a new integration rule. You just needed a new technique, right? We just made a couple of substitutions and turned it into something we can integrate really easily. And then we put the thing back and we're done. All right, let's go to a boatload of examples to try to get good at this now, right? And on the way, Mr. Kulik can show you some of the little tricks of things that like, oh, what if that happens? How can I still cram this substitution rule through? Okay, so let's go ahead and look at our next one. The integral of x cubed times cosine x to the 4th plus 2 dx. What should we pick for u on this one? X to the 4th plus 2 is correct. When I take the derivative of u, we get, you mean 4x cubed? Or, and if I multiply both sides by dx, I get that, right? Now we have a little bit of an issue here. So I see, okay, well, x to the 4th, I can just replace with u. And I have an x cubed and a dx that I can replace with a du. But what about that 4? if I just divide it to the other side? And now I can replace x cubed dx, which is du over 4. Does that feel okay? Chanel, what's up?
Wait, so how'd you get the du over dx equal 4x cubed?
I just took the derivative of u.
Is that what like du dx is?
Yeah, the derivative of u with respect to x.
Okay.
Is this okay? Now the du over 4 is no big deal because I can just take that 1/4 as a constant out front. And I'm really just doing the integral of cosine u du. What's the antiderivative of cosine? Positive sign, thank you. And then we got to have plus c though, right? And then we just plug our u back in. And we should be good. What do you guys think? So if your du differs by a constant, like it did in this problem, not a big deal. We just divide the constant over and we have, du times a constant or divided by a constant, whatever you needed to do to make it work. It's fine, not a big deal. So far, so good? Okay, let's try another one. Yes? Okay. So what if we want to do the integral of the square root of 2x plus 1 dx? What should our u be in this case? 2x plus 1. And the derivative of u is 2. So when I multiply the dx over, du should be 2 dx. What do I need to do, though? Divide by 2, because all I have is a dx, not a 2 dx. And now I'm in a form where the integration should be pretty easy. Right? We'll pull the 1/2 out front. I'll rewrite square root of u as u to the 1/2. What's the antiderivative of u to the 1/2? Don't forget our plus c's. Let's see, that 1/2 multiplies through and cancels the 2 down there. So we have 1 plus 2x. No, it's 2x plus 1, wasn't it? I guess it doesn't really matter. Let's be consistent though, right? How's this feeling so far? It's not bad, right? Okay. Let's try the next one. The integral of x over the square root of 1 minus 4x squared. What do you think for the u?
Would it be 1 less x?
I think that's what I would try. So the derivative of u is? Good. So du should be negative 8x dx. Now I see the x dx in the problem. What am I missing though? The negative 8. So all I do is just divide that over to the other side. So when I make my substitution, I have 1 over the square root of u times du over negative 8. Is everybody okay?
Wait, how do you have 1 over the square root of u? You just, like, so 1 minus 4x squared is the u, so.
So this is my u. So that it's in the denominator of fraction, right? What's in the numerator of the fraction now? 1, because the x dx is the du over negative 8 part. Does that feel okay?
Yeah.
So let's see, we can pull that negative 1/8 out front. I'm going to rewrite that 1 over the square root of u as u to the negative 1/2. What's the antiderivative of u to the negative 1/2? And then plus c. So I multiply these two guys together, they reduce to 4. So I have 1 minus 4x squared to the 1/2 over negative 4 plus c. I guess the negative could just be like out front, wherever. Doesn't have to be in the denominator by any means. Someplace, though. And again, you could write that as a square root instead of the 1/2 power, whatever. All right. Let's try another. E to the 5x dx. Five x seems like the natural choice. So du should be 5 dx. I don't have a 5 dx, I just have a dx. So we'll divide both sides by 5. Everybody feel good there? What's the antiderivative of e to the u? E to the u, and then we just have plus c. And we plug our u back in. And we're done. All right, you ready for the tricky one now? Okay. What should our u be? Okay, 1 plus x squared. And du dx then is 2x. So what should du be? Now I don't have a 2 anywhere up there. Now what's the problem?
You saw the x to the fifth.
Well, I don't have x to the 5th. I'm going to have an x to the 4th, right? Because one of those x's is out with the du over 2.
That's so stupid.
With u being x to
Nope.
the fifth.
We got to do... So we do have a problem here, right? What's the problem?
The x.
We still have an x to the 4th. We have 2 different variables, right? Somehow we have to rewrite that x to the 4th in terms of u. This is going to be my trick. That's what I'm going to be using. So I'm going to subtract 1 from both sides. And if I square both sides, u minus 1 is x to the 4th, right? And now I'll substitute that into there. And now we're going to be good to go because now we have just u's. Again, coming up with that on your own the first time without ever seeing it, that's pretty sneaky. As you've seen that as a trick you can use, you will have to use it in your homework. You'll see this happen in the problems. So if you do your initial substitution and you don't get rid of all the variables, you might have to do a second round of rearranging your u and do a substitution again. That is not uncommon. All right, but how am I going to integrate the square root of u times u minus 1 squared? You have every tool that you need to do this problem right now at your disposal. Do you know what to do as it's currently written? No. So what should you do then?
Make the square root of half.
Okay, what else should you do? Foil that out, right? If you can't integrate it as it's currently written, try rearranging it to get into a form you can integrate. What should we do from here? Still not ready to integrate it yet. Distribute. So 2 plus a half is 5 over 2. 1 plus a half is 3 over 2. And now, can we integrate that? Yes, because each one of those you can just use that power property. Because we can integrate term by term. So 1/2. What's the integral or the antiderivative of u to the 5 over 2? Over 7 over 2. And then what's the antiderivative of u to the 3 over 2? Yep. And how about the antiderivative of u to 1/2? And then we'll put 1 plus c at the end. So when I distribute, yes, Pierce.
You were saying that you're distributing, it was over to the left a little bit, where you get the power from, that's 5 out of 2, and 3 out of 2.
Yeah, just made common denominators.
Oh.
Like 1/2 plus 2 is 5 over 2.
Yeah, okay.
1 plus 1/2 is 3 over 2. So I'm going to distribute through that 1/2. When I do that, those guys cancel, and you just have 7, 5, and 3 as your denominators. And that's probably where I would leave it. Oops, that's minus. I wouldn't bother with making any common denominators, anything at this point. That looks fine to me. Oh yeah, then we should plug our u back in, for sure. Thank you. Forgot to do that. What was our u again in this case? 1 plus x squared. That's right. So long ago. Thank you, Talika. You're going to be a pro at this already. That's our answer. That's kind of the worst case scenario when you have to do like 2 rounds of u sub. Well, again, these are the kind of problems that make sure you're being careful about showing your work. But if you kind of just go through carefully, they aren't too difficult. But it's easy to, like, if you're your work is kind of scattered and you like to skip steps and you're kind of messy, you can run into some problems doing this sort of thing because you just kind of forget what was what. All right, let's do one more. The integral of tan x dx. Now remember, on your antiderivative rules, there is no antiderivative for tangent on our list, right? So what are we going to do? We'll rewrite tangent as sine over cosine. Excellent idea. So which one do you suppose we want to make u? I would not do 1 over cosine. I would just do cosine. And in general, I'm usually going to pick the denominator. Why? What do I get when I do the derivative? Negative sign. So I should have negative du is equal to sine dx, right? Notice that I have that right there. If I had, instead of picking u to be cosine, if I picked it to be sine, I would end up with 1 over cosine times dx, which is not what du would have equaled. Very easy to make that mistake, to like think about them as, not two things. But in general, we're thinking about this as like sine x times 1 over cosine x. Where's the function composition at? It's the cosine that's plugged into 1 over x, right? If you think about it that way, it's like, oh, of course that would be the u. Okay. All right. Let me erase this, get that out of the way. Okay, so we have integral 1 over u times negative du. What's the antiderivative for 1 over u? Well, I guess I'll do that. Anybody remember?
Mr. Blue, can I have a question?
What is it, Chanel?
Oh, I'm sorry.
That's okay.
Why'd you make the u cosine x?
So if I think about sine x over cosine x as sine x times 1 over cosine x, where's the function composition at?
Oh. I'm
Cosine
so
is plugged into 1 over x.
I'm so sorry.
That's okay. Braden.
These natural log?
Close. Natural log of the absolute value, x. Why does the absolute value have to be there? Oops, I meant u there, not x. We can't take the natural log of non-positives. So 0 or negatives are both problems. That's why it's an absolute value there. So we'll plug back in, right? So our u was cosine. So this answer would be okay for me, but we can do a little better. Who remembers their rules for logarithms?
Not me. That's for sure.
So I'm going to imagine that's a -1 as my coefficient there. What's a coefficient in a logarithm equal to? An exponent inside the logarithm. That's right. So what's cosine to the -1 equal to? Okay, 1 over cosine, which is secant.
Wait, but we could have it at Liverpool.
This would be okay for me,
Okay.
but I'd assure you on a multiple choice test,
It's not
that would not be one of the selections. I just want to cover our bases, right? I want to be clear about like what my expectations are and what like a multiple choice expectation are, because the difference between a free response question and a multiple choice question are different, right? Multiple choice question, you have to get to a specific answer, one of the ones listed. A free response question, to me, you just need to finish the calculus. And then the simplifying is we check that during the multiple choice. You know what I'm saying? Okay. Yes, sir.
So how come, when you write over there on the left-hand side, where your equation was 1 over u times du, and then
That's times negative du.
right, yeah, and then like how did you get from there to just turning it into a c, so like plus c at the end? There's a 1 over u part of it, but then where did the du go?
Well, here I have the negative integral of 1 over u du.
Yeah.
Here the integration is done. So the integral symbol and the du go away when I compute the antiderivative.
Oh.
And I'm replaced with, and I get the plus c after the antiderivative is calculated.
But then the du would be equal to sin x times dx.
Right? Like if I just do the integral of x dx,
Yeah.
that's x squared over 2 plus c, right? Notice the dx and the integral symbol are gone because I've done the
Oh,
integration.
okay, yeah.
That's all that's happened there. Does that?
Yeah, that makes sense.
Okay. Okay. So up to this point, we've only talked about indefinite integration, right? Where there's no bounds attached to our integral symbol. What if we're doing this same problem as a definite integral?
Solve that.
So you can do what we had been doing. We can solve the indefinite integral, plug our x back in, or plug our u back in, add the real bounds on, and then finish the problem. Or, what is often simpler, particularly if you have no calculator option, is you can compute new bounds that are in terms of u. And you never have to substitute u back in. Typically, that's going to make the calculation simpler, and in a no calculator situation, can save us a little bit of hassle. So let's look at how this is going to work both ways. So this is a problem we've already done, right? we said here u should be 2x plus 1. Du over 2 should be dx. So the integral of square root u times, well, 1/2 du, and that became u, or 2u to the 3 over 2 over 3, or yeah, over 3, and we substitute back in. And then we evaluate that now from 0 to 4, because it's a definite integral. And then you continue grinding that down, right? Alternatively, and again, in a no calculator setting, I think this tends to be easier. I'm going to redo the bounds. So I'm going to take the 0 and I'm going to plug that into u. And I'm going to take the 4 and I'm going to plug that into u. And now I'm going to integrate from 1 to 9 square root u du, which gives me 2u to the 3 over 2 over 3, or evaluated at from 9 to 1. And notice if I'm doing it this way, I'm never plugging my u back in. And just like the arithmetic's a little bit neater, a little bit cleaner, right? U to the 3 over 2, the square, or I'm sorry, 9 to the 3 over 2. Square root of 9 is 3. 3 to the third is 27. 27 divided by 3 is 9. Times 2 is 18. 1, the square root of 1 is
1.
1 cubed is
1.
Times 2/3 is,
2/3.
so this is going to be like 17 1/3 or something. Done. I like doing it that way, especially if I'm not gifted a calculator. I think that just like less substituting I have to do, I think the better. You know, I'm just going to change the bounds right away and go on about my business and never look back. Nothing ever has to turn back into X's. Just all stays U's. And the nastier your choice of U is, really the more benefit this method holds, right? Like if your U is gross, the grosser U is, you know, the better this looks. Okay, let's try again. Our u here would be 3 minus 5x. So my du dx is -5. And then du is -5 dx, but that doesn't work for me because I don't have a -5. So I have that. And now I'm going to do u of 1, the lower bound. And then u of 2, the upper bound. I feel okay? So we're going to be integrating from -2 to -7, 1 over u squared times du over -5. What do you notice that's weird about the bounds for my integral here? The top one is the smaller one. Yeah, Pierce nailed it. How can I switch that to make it look more standard? Yeah, if I negate the integral, I can flip the bounds. Now, I'm going to also pull that negative 1/5 out front. So I just can turn the whole thing positive now. Everybody's good with where the negatives went to? Okay. Oops. du. And now let's do our antiderivative. The antiderivative of u to the negative 2 is? And then we'll evaluate that from negative 7 to negative 2. So I have 1/5 over negative 1 over negative 2 minus negative 1 over negative 7. Or what do I got? I got should be positive 1/5. I don't know why I put a negative there. Okay, so it's going to give me 1/10 minus 1/35. And if you want to make some common denominators with that, go right ahead. I think I'm done here. Well, it would be 25 over 350, and you could do some reducing. I think it comes down to like 1/14 is what it looks like to me. You got it? Feel okay? I'm going to just skip this next one in the interest of time. So, two little handy shortcuts. We love shortcuts, right? So it says if f is even, remember what an even function is?
Yeah, a long time ago, but yes.
So it means that f of negative x should equal f of x. Yeah. Or if you think graphically, it's going to look like a reflection across the x or the y-axis, right? If that's the case, and you're integrating from that even function from negative a to a, well, if we think about it, if you're thinking about like x squared, this area and that area should be the same areas, right? So I'm just going to do 2 times the area here. That's all we're saying. Does everybody feel okay there? Okay. Now, if we have an odd function, what does an odd function look like graphically? Yeah, that's it, Braden. So it'd look like this. So if I look at that area and that area, what do you notice? One of them's a negative and the other is a positive, but they both have the same magnitude. What should the area under the curve then be? 0. That's a massive time saver. And I often see an AP exam question where they give you some terrible integral with an odd function. It just goes from like negative 1 to 1 or something. And they don't really expect you to do the integral by hand. They expect you to just notice that, hey, this was an odd integral and 0. Popular on a multiple choice question. Particularly, it could even give you an odd function where you're unable to do the integral by hand.
That's no calculators.
And so you can't, and if it's no calculator, you can't just type in your calculator to get the number. You have to remember this shortcut here. Yes, Chanel.
Maybe on the graphic?
Sure. All right, let's look at a couple examples. The integral from negative 2 to 2 of x to the 6th plus 1 dx. That's my immediate cue to start thinking about this. Yes. Is x to the 6th plus 1 even or odd? How do you know? The degree of the polynomial alone will not tell you if it's even or odd. So what's the degree for that term? 6, which is even. What's the degree for that term? 1 is incorrect. 0. Why is it to the 0? Because there's an x to the 0 at the end. 0 is even. The sum of even functions is even. So that is even. And as a result, you could just do this. You could do that, which is not a terrible time saver. And that's good enough, I think, for us, right? I'll leave common denominators to you guys. Although it is nice having the 0 there, right, for plugging in. Oops, we forgot the 2 there. Right, sorry. I forgot the 2 from the formula. Yeah, just from the formula. All right, let's take a look at another one. Whoa, is what Talika says. So, tangent of x, odd or even? What's the graph of tangent look like? Just the first period. Looks like that, right? Odd or even? Okay. 1 plus x squared over, or 1 plus x squared plus x to the 4th. What's the degree on 1? What's the degree on x squared? Also, so again, worth pointing out to you guys, even function plus even function plus even function plus even is still even. Even plus odd? Neither. Neither. Odd plus odd plus odd? Odd. Doesn't matter how many odds you add together, it's going to be an odd function. Yes. Because if you think about it, if you have like... Nope. Nope. We're not adding numbers. We're adding functions. That's okay. And since they're both odd, you can do this. Right? So even the sum of 2 odds is still odd. Everybody agree? Okay. Odd over even. It's odd. So again, if you think about it as odd over even, if I do f of negative x, I'd have negative g of x because it's odd, and just regular h of x because it's even, that is negative f of x. So odd over even is odd. Odd over odd would be even, because the negative signs are going to cancel out, right? The negative on top would cancel with the negative on bottom, right here. And then even over even is even. The same rules would apply for multiplication. Odd times even is odd. Odd times odd is even. Even times even is even. It's not, we're not, it's the rules for multiplying functions is not the same as multiplying numbers, right? Like odd function times odd function is odd function. Odd number times odd number is odd number. right? So the rules for that is different. But in this case, we notice that this is an odd function then, so just the integral 0.
So instead of thinking about like odd numbers and even numbers, is it like better to think about it as like negative signs and
Yeah. So an odd function is basically a negative sign, and an even function is no negative.
Is that why a negative plus an even is like neither?
Because the sign doesn't change for both of them, or doesn't stay the same for both of them. Exactly. Yes. So that's it for this section. I think, again, fairly doable, right? This was not mega complicated. Little symbol pushy, but not too bad once you get the hang of it. Again, this odd even thing, I would guess 1 to 2 questions total on an AP exam might have to do with something like this. It's not a huge piece of it. Again, if you forget it, it's often still doable, even if you've forgotten this property, but it can be a big time saver if you catch it. That's the takeaway. So even functions, let's just review real quick. Let's just say, oh, come on, stupid thing. I don't know, just trying to write down some of this odd even stuff so it's in one place for you. That's all I can come up with off the top of my head. I can't remember the inverses. I think the inverse sine and cosine and tangent match. Yeah.
You're saying monomial with even degree usually like 2x squared, right?
Uh-huh.
Okay.
Or just x to the 4th or 7. Because if I take cosine and I reflect it across the line y equals x, I think I get the same symmetry. Let me look. I don't know, maybe that's neither. That's odd, but sine was odd before. I think they stay the same, maybe. What?
No, I was confused.
Think about the graph. So like the graph of cosine looks like that, where it's even, symmetric across the y-axis. But the graph of sine is like, yeah, it's like that. So it's odd. We didn't take any questions from homework. Did you guys have, I forgot to do that at the start. Did you guys have homework questions we want to talk about? $128. That must have supposed to have been 118. No. I did put up some test info. At least I've started writing the test. This is what I have so far.
What's an integral?
Well, just like a problem I wrote that's not based necessarily on like an AP question.
Is it just like you're solving an integral and you're
Yeah.
evaluating it? Is that like 5.3, 5.4, like fundamental math? Like that,
Yeah.
That stuff?
Yeah. Or you might have to like calculate areas from a graph or approximate it with a Riemann sum from a table. You know, like those are all integral problems.
So for the MCQs, should we just practice the 40 you posted?
Yeah, I think that's a good plan. I would say here also, guys, have you guys looked at MCQs or FRQs yet? Little bit. Try to do some before next class. We'll take some questions from that next class also. I have keys for these. I just want to give you guys a chance to work on stuff before I give you keys. I think Friday we'll do like a review game based from the MCQs and FRQs.
What is the winner again?
Pride. Bragging rights. So if you have a chance to look at those in advance of tomorrow or Friday, that'd probably be good. Some of them are pretty straightforward. Some of them are quite challenging. There's some tricky things in there. But I think in general, they're pretty straightforward in terms of what they're asking. There's like one or two that are like, ooh, how do you do that? Like I thought about in first read, I'm like, how do you do that? And then I had to think I'm like, oh, okay, yeah, it's not as bad. Not that bad.
Are there any textbook questions we should study or not for this?
I haven't gotten anything together yet. I still,
Oh, okay. That's
again,
fine.
like I'm still in the rough draft mode. Like I wrote a draft and then I've been like proofreading and editing it. And then I'm going to go back to be like, okay, what is this like? What would this be similar? What was this similar to? Because it's stuff like we've done.
Okay.
It's just like, finding the thing it's most similar to. You know what I'm saying?
Yes.
And sometimes that's a struggle. Because sometimes it'll be like, oh, it's kind of like similar to this question from this section and this question from that section and that question from that section. Because it's like, like 3 stages of something.
Yeah, like parts.
Yeah. Like if I ask you to approximate something and then find the indefinite integral and then find the definite integral for it, like that's like 3 parts of like doing the same thing, but it's like 3 sections of kind of questions that it would be similar to, kind of, you know what I mean?
Yes.
So, again, I'll get more specific on this as I go, but this was just like me kind of sketching something out as I was writing it. Once I have a firm, finalized version, I'll get you guys more specifics, but I figured somebody's going to want it earlier, so I'm just giving you what I have right now. You know what I mean?
Yes.
Okay. How's everything else going? So just as a reminder, again, next time we're going to do 6-1. 6-1 is pretty short.
Rectangles.
No, it just areas. It's just integrals, guys. It's actually pretty easy. It's actually pretty easy because you're just looking at the area between 2 curves, which is not bad. The next section we'll be looking at volumes. Which again, the first section on volumes is pretty easy.
I got a 13.
This section 6.3 is the hardest one for the next test.
6:30.
Yep.
How many chapters are we getting through this year? Or like this semester?
Well, we're going to do parts of chapter 6. We'll do all of 5. I think we do all of 6. We'll do parts of 7, parts of 9, and maybe parts of 8.
What do you think is the hardest remaining?
I think for students, it probably tends to be this volumes of revolution idea. Again, this will vary depending on like how good is your three-dimensional imagination. If you can imagine what the thing looks like, it makes it much, much easier to come up with like a equation for the cross-sectional area. And if you're able to do that, the integration is easy. The setup is the hard part. Much in the same way that like the related rates problem, the setup was the hard part. When you actually like do the derivative and plug the stuff in, that's usually pretty easy from there. But the setup was the hard part. Similar in that regard. And then to complicate this, there's like 2 different techniques that you'd use, and depending on like how the function's behaving, you have to be able to choose which technique would be appropriate, which one wouldn't. So this tends to be the hardest thing in test 2, and might be the hardest thing in second semester, is this topic. But again, once you've gotten the hang of it, all the problems are basically the same. Unlike the related rates problem, where like, depending on the shape of the thing and like what's going on, the tricks could be fundamentally different. Here, there's only like 3 tricks you can do. And it's like, that's it. Like they all kind of look like one of these 3 things, and it's done. It's not so bad.
Yeah, but later rates are so bad.
What's up?
Oh no, I noticed a little frowny face. I can't do that without looking it up.
The frowny face.
Yeah, the frowny face. This is going second variant. Up, go down.
Yeah, yeah, oh, yeah. It's up, yeah. Right
Oh, yeah.
Yeah. You can't do it.
If we seriously?
Yeah, I can't do that without looking it up. To rewrite that as x equals in terms of y. It's a cubic, so there's like a closed form cubic formula. It's a polynomial. It's solvable. It has a solution. But like, I can't do that.
Yeah, no, that's
okay.
Right? This is an example of a problem that you have to do a different way than the previous method.